Attributes of polynomial functions. So first, let's look at what standard form is. So standard form is when the terms are arranged by degree in descending order. So for example, f of x equals 4x squared minus 6x to the fourth plus 5 minus 4x. So we want to look for the term that has the highest degree. That's the highest exponent. So the highest exponent that we see is 4, so the highest degree is 4. So this term, negative 6x to the fourth, will go first, negative 6x to the fourth. And we'll look now for the next highest degree, or next highest exponent, that's 2. So 4x squared will go next. And then this last term, negative 4x, actually has an exponent of 1. That's our next term, because that's the next highest exponent. So negative 4x goes next. And then we're left with our constant, plus 5. And remember, our constant can be written here as 5 times x to the 0 power. So our constant has a degree of 0, because x to the 0 power is 1. So this first term that had an exponent of 4, negative 6x to the fourth, this is our quartic term. We don't have a term that has an exponent of 3. That would be our cubic term. Our 4x squared is our quadratic term. Our negative 4x is our linear term. And our 5 is our constant term. So we can create a table. So a term with degree 0 is our constant. For example, 5. A term with degree 1 is a linear term. For example, 4x. A term with degree 2 is a quadratic term. For example, negative 3x squared. A term with degree 3 is a cubic term. For example, 42x cubed. A term with degree 4 is a quartic term. For example, negative 16x to the fourth. A term with degree 5 is a quintic term. For example, 32x to the fifth. And there may be other commonly used terms, but these are the ones that I most commonly hear. If other ones are used, I don't really hear them. So you can classify a polynomial by its highest degree term. So for example, 6x cubed minus 4x squared plus 5, its highest degree term has an exponent of 3, so it's a cubic, and it has 3 terms, so it's a trinomial. So we would say that this is a cubic trinomial. If it had 2 terms, it would be a binomial. If it had 1 term, it's a monomial. So some new attributes are end behavior, and this describes the direction of the graph to the left and to the right, and we'll see that in a moment. Turning points, but we can have more than one. A point where the graph changes direction from up to down or down to up. And we've seen one of those before when we've looked at quadratics. So for example, a vertex. So for example, let's identify the end behavior and turning points for y equals 2x squared minus 3x minus 2. So here's its graph. So the end behavior, we can see on the left side it's pointing up to the left, and on the right side it's pointing up to the right. And you can also see end behavior written using infinity notation. So we could write as x goes to negative infinity, as my x's go to the left, the y's go to infinity, the y's are going up. And as x goes to positive infinity, as the x values go to the right, the y values are going to positive infinity, the y values are going up. The turning point here is down here, the vertex. So to find the vertex, because it's a quadratic, we can use what we know about quadratics. A is 2, B is -3, C is -2. We can find the x value of the vertex by taking the opposite of B over 2A. So the opposite of -3 over 2 times 2, which is 3 over 4. Or we could, because it terminates, we could convert it to a decimal, which is 0.75. To find the y value of the vertex, you could do 2 times 0.75 squared minus 3 times 0.75 minus 2. And that equals -3.125. So our vertex has the coordinate 0.75, comma, -3.125. And over here on the left, this is where our function is going down, where it's decreasing. So the function's going down to the left of the turning point, and to the right of the turning point, it is going up. So the turning point is where it changes direction. Our turning point was 0.75, comma, -3.125. The function is decreasing where it's going down, and we're looking at the intervals of the x values. There could be more than one interval for decreasing and increasing. Here, for the quadratic, we're just going to have one of each. So the x values where this function is decreasing are from -infinity up until 0.75, the x value of the vertex. And the function is increasing where it's going up. And for this function, it's going up from 0.75 to infinity. Okay, let's look at another example. Identify the end behavior and turning points for y equals 2x cubed minus 3x squared plus 1. So here's our graph. So for the end behavior, we can see on the left, it's going down. On the right, it's going up. So it's down and up. Or using the infinity notation, we could write as x goes to -infinity, as the x values go to the left, y goes to -infinity. The y values go down. And as x goes to positive infinity, as the x values go to the right, y goes to positive infinity. The y values go up. So turning points. So to find turning points of polynomial functions higher than quadratic, we actually probably haven't seen the math yet in this course. And to find the turning points of many much more complicated functions, we would probably need calculus. For some, like this one where the turning points are intercepts, we'll see a little bit later on in the course. But these are intercepts, so we can look at them from the graph. But we see the function is going up here to the y-intercept at 0, 1, and then it goes down. So a turning point is 0, 1, and then it changes and goes up again. And so it has a turning point here at an x-intercept, at one of its x-intercepts of 1, 0. It does have another x-intercept, but that's not a turning point. So our two turning points are 0, 1 and 1, 0. It's increasing. Now we have two intervals where this function's increasing. Remember, we're looking for the x values. So the first interval is from -infinity up to 0. So it's going from -infinity up to 0, which is the x value of that first turning point on the left. And then it's also increasing from 1 to infinity. So if we look at that second turning point, where it's starting to go up again, that x value is 1, and then it continues to infinity. Again, we're considering the x values. So this function is decreasing in between the two turning points. So we're looking at the interval of the x values between the two turning points. So from 0 to 1. So you can also determine the end behavior of a polynomial function by looking at its equation in standard form. We don't need to see its graph. All we need to do is look at its leading term. And that leading term is represented by a times x to the n. So if I create this table, we're going to have our n's are the exponents. We can have n be even or odd. And we're not considering n as 0. And then a is the leading coefficient. It could be either positive or negative. So if the leading coefficient is positive and the degree is even, the polynomial function will have end behavior of up and up. If the leading coefficient is positive and n is odd, then the end behavior will be down and up. If the leading coefficient is negative and n is even, then the end behavior will be down and down. And if the leading coefficient is negative and the degree is odd, then the end behavior will be up and down. So for example, if we have y equals negative 3x cubed plus 4x minus 1, we need to look at the leading term, which has degree 3. That's our n. 3 is odd. So we're looking in the odd column. And our leading coefficient is negative 3. So that's a is less than 0. It's negative. So we're looking for the cell that's the intersection of those two, of that row and that column. That means this function has end behavior up and down. So y equals negative 3x cubed plus 4x minus 1 has a graph that points up on the left and down on the right.